Okay, so here we're going to be deriving a relation between the osmotic pressure, capital Pi, and the molar concentration of the solute, or B. So there are going to be 4 steps to this derivation. The first one will be to write an expression for the chemical potential of the solvent in the solution. So that will be equating the chemical potential of the pure solvent with the chemical potential of the solution, which includes both the solvent A and the solute B. Step 2 will be to evaluate the effect of pressure on the chemical potential of the solvent. So that will be done using some earlier equations relating Gibbs free energy with changes in pressure. The third step is to evaluate the resulting integral, and the fourth step will be to simplify the expression in terms of the osmotic pressure and the concentration of the solute. So essentially the setup is something like this, where you have a container and you have 2 compartments, and let's suppose you also have some sort of, let me draw it, okay, never mind, some sort of piston on both sides, with this piston applying a pressure P, and this piston on the right applying a pressure P plus capital Pi, or the osmotic pressure. So say that this membrane here, or this sort of divider, is semi-permeable and it allows only the solvent A through. On this left you have a pure solvent, and on the right you have the solution of solute B and solvent A. So what you want to know here is that the chemical potential of a solution when you add a solute is most likely going to be lower or less than the chemical potential of the pure solvent. If you think back to the relation mu A mu A is equal to the chemical potential at pure A plus RTLN, and then the molar fraction of A. So if you have a solution, this molar fraction is going to be less than 1. The molar fraction is less than 1. Ln of a value of less than 1 is going to return a negative value. This will decrease the value of the chemical potential of A with respect to the pure chemical potential. So the lower a chemical potential is, the more stable it is, essentially. So that means the solvent is going to want to go towards this lower potential from a high chemical potential. So it wants to change to a lower potential where it wants to be more stable in relation to the higher potential. Sorry if that was confusing. But essentially you want to know that the solvent wants to go into the solution for mainly entropic reasons. And that's why you have this lower potential, chemical potential, on this right side. So assuming that this pressure here is 1 bar, we're at standard conditions, so the chemical potential on this left side is going to be mu A standard, where the star is equal to standard. So at 1 bar, the chemical potential of A at 1 bar, and this is going to be a liquid with respect to a pressure P. So on this right side, we have a solution. Your chemical potential is going to be mu A with respect to, not with respect to, but in terms of pressure P plus osmotic pressure. So what you kind of want to know here is that at equilibrium, so say that you have this sort of setup and you let it run to equilibrium, essentially you're going to have zero net flow only when these two potentials, this one and this one, are equal to each other. So your standard chemical potential is going to be equal to your non-standard, or your solution, or your chemical potential in a solution at this increased pressure. So we already kind of talked about what adding a solute would do to the chemical potential, but adding osmotic pressure will essentially raise the chemical potential, just in a sort of mathematical sense. XA is equal to PA over P star in ideal solutions, but usually you have, instead of this XA value, you can substitute that in for a PA over P star. And then if you add an osmotic pressure right here, that's going to make this fraction greater than 1, and then this natural log is going to return a positive value, and then your chemical equilibrium is going to be greater than the standard. So you have these two opposing forces, the solute, which decreases your chemical potential, and then the addition of osmotic pressure, which will increase your chemical potential. So here you have this equation, because you are at equilibrium between this membrane and this setup. Alright, we also want to, so here we have that pressure value. We also kind of want to express the fact that this isn't a pure solution. So say that XA with these parameters. So you have your XA, your mole fraction, and then this change pressure. So your standard and then your unstandard. So what you kind of want to remember is that we already have a sort of equation to reflect this change in chemical potential as a result of the change in mole fraction, or in terms of the mole fraction. That's kind of this equation that I kind of mentioned earlier. So it's going to be mu A with the parameters of the mole fraction of A at pressure, P plus osmotic pressure is equal to your standard at pressure plus osmotic. So I mean, in this case your standard isn't going to be 1 bar, but you know, whatever. So now you have that, and I want to add this also, because that's part of the equation now. So here's your sort of equation. I want to substitute that in for here, and then you're going to end up with mu A at pressure P standard is equal to mu A standard P plus osmotic pressure plus RT, natural log of the mole fraction of A. Now you're just going to want to rearrange in terms of this, and then you're going to get this expression. Sorry, the stars are pretty terrible. Okay. Alright, so that's step 1. We've written an equation that relates the chemical potential of the solvent in the solution. So step 2 is to evaluate the effect of pressure on the chemical potential of the solvent. So in order to relate the pressure with the chemical potential, you're going to want to remember this formula, where the molar Gibbs free energy of the final pressure is equal to the molar Gibbs energy of the initial pressure plus the molar volume of the solvent or the liquid, or whatever you're evaluating, times dP evaluated over the integral of the initial pressure to the final pressure. So what you kind of want to recognize here is that the molar Gibbs free energy of the final pressure is equal to your mu A standard at the final pressure being the initial pressure plus your osmotic pressure. Also, the molar Gibbs free energy of the initial pressure is going to be equal to the chemical potential at your starting pressure. So you're going to want to make these substitutions, this one here and then this one there, and then what you end up with is this expression. So the final pressure will be this pressure plus osmotic, and then pressure. Also, it's like 3:44 a.m. I don't know what I'm doing. So your initial pressure is going to be this P, and your final pressure P plus capital pi times your molar volume dP. So what you also kind of want to know is that we actually have an expression for this in terms of this. So you scroll back, it's right here, and you're going to want to make that substitution so we can simplify further. So plug it in and you get your standard chemical potential of molecule A or solvent A at the initial pressure minus RT natural log of the mole fraction of A is equal to the chemical potential of A standard at P plus this integral molar volume of the solvent with respect to change in partial pressure. So what you kind of want to recognize here is that this appears on both sides of the equation, and you can cross out this standard chemical potential term, and we can simplify to this negative RT natural log of the molar fraction of A is equal to the integral of the molar volume of the solvent evaluated over P to P plus osmotic pressure with respect to partial pressure. So we also kind of want to make the assumption that Vm is constant over the change in pressure, or from P to P plus osmotic pressure. So that allows us to pull it out of the integral. To pull it out of the integral. So let me just rewrite that real quick. Negative RT natural log of the molar fraction of A is equal to the molar volume of the solvent multiplied by the integral of dP evaluated over the limits. So we can just do this quick integral. It's equal to the molar volume multiplied by P plus osmotic pressure minus P, and then cross that out, is equal to molar volume times osmotic pressure. So you're sort of, oh, this is step 3 by the way, the evaluation of the integral. So you end up with RT ln natural log of the molar fraction of A is equal to the molar or osmotic pressure times the molar volume of the solvent. So you end up with this. Since we essentially want to end up with this molar concentration of the solute, we're going to want to change this to be expressed in terms of the molar fraction of B. So you just want to know that the molar fraction of A is equal to 1 minus the molar fraction of B. We'll make that substitution. Okay, so here we also want to make the assumption that we are in a dilute solution. This means that the molar fraction of B is much less than the molar fraction of A. So imagine just a bunch of A solvent particles or molecules surrounding very small amounts of this B molecule, this solute. So just A approaches 0, it's very small, very small. So the approximation that we make here, that xB approaches 0, allows us to make the approximation that the natural log of 1 minus a really small number is going to be that really small number. negative. The sort of just makes sense. Here's the plot, the natural log plot here. Here's 1. Say that this value is very close to 1, so right here you're gonna get a really small negative number. And that small negative number approximates to this negative xb, or whatever you subtracted your 1 from. So that's sort of the intuition there. So let's simplify a little bit. Negative RT times negative molar fraction of B is equal to the molar volume times the osmotic pressure. I should have done this earlier. Let me just apply that. Okay, here you go. Here you'll notice that we can finally get the molar concentration of the solute, which is divided by molar volume. So RT xB. Okay, I'll just write it out so it's clear. It's equal to the osmotic pressure, RT, molar concentration of B, moles per volume of solvent is equal to the osmotic pressure, and there you have it. Simplify. That's a terrible form. Simplify. So the osmotic pressure is equal to RT times the molar concentration of B, and there is the expression. This is also called the Van 't Hoff equation, and it's applicable only for ideal solutions. Right, so that's that. This is the expression which relates the osmotic pressure right here with the molar concentration of solute.